Hi, this is Brian again. I want to take some time now to talk a little bit about the tools in StatCrunch for calculating normal probabilities. In particular, really, it is called the normal probability calculator. And I want to show you how versatile it is and how handy it is for answering a number of different questions that you'll be asked about. Okay, so first of all, this is the kind of a standard type of question. Uh, if you have a standard normal random variable, we're going to very often, if not always, refer to a standard normal random variable as capital Z. You're interested in the probability that Z takes some value in some interval. Okay, so just take a look at the problem. First of all, we're looking at the distribution of Z. Okay, now I want to show you in StatCrunch how to get to the probability calculator, and then we're going to do some work in it. So under the Stat menu, click Calculators, and you want to go down to the Normal calculator. Normal probability calculator is going to look like this. We have a standard view, not to be confused, unfortunately, with a standard normal distribution. Standard is we're interested in area to the left or area to the right. Between is area within an interval. So let's first just look at the different parts. You have this image shading an area in red that we're interested in, and then we can specify the mean of the distribution, the standard deviation of the distribution, as well as we can have some inputs for calculating probabilities. So if we're talking about a standard normal distribution, that's a mean of 0 and a standard deviation of 1. So looking back at the problem, we're looking for the probability that Z is greater than 1.34. So don't worry that we have X instead of Z in the probability calculator. This is generic, but we're looking for the probability being greater than, just type in click greater than, and then 1.34, click compute, and this gives you a nice shading of the probability as well as a calculation exactly of what it is. So you can copy that. Let's just put it in. Okay. The probability that Z is less than, so to choose less than, change the sign from greater than or less than, type in the negative 0.37, click compute, and we're in business again. We can copy that probability. Now for the probability that Z takes a value between, you go to the normal calculator between and put in your two values, 0.08 and 0.57. Compute, get a nice picture, you get your probability. Now for a probability in the tails, this is the probability that Z is either less than negative 2.4 or greater than 1.78. One way that you can do it is you can calculate the area. Say first you can go less than negative 2.4, compute that, and I'm going to just put that into my calculator. So we have this probability is 0.0081974, and then we can go greater than 1.78, compute that, get our other tail, 0.0375, 3798. That will work. So you can get your answer 0.0457352. This will work. Another way you can do it is to use the between calculator and to put in the two values, negative 2.4 and 1.78. Now this is going to calculate the area between, but what you can do is take this, because you know that the total area of under the curve, the total probability is 1, you can find the area out in the tails by subtracting this from 1. So we can type 1 minus 0.95426 and we'll get our answer that way as well. So both ways will work. Both ways will give you the correct answer. I think this way is a little bit easier, so I'm going to do that for the next example. Speaking of which, the next example, we have a normal distribution where we have, it's what we would call a non-standard normal distribution, but we can enter the mean and standard deviation in here, a mean of 23, a standard deviation 2.76, and we can calculate our probabilities the same way. The probability of x being greater than 25, easily done. The probability that x is less than 1.94, just type it in, or 19.4. Oops. Easy. Probability between. We want to go between 18 and 22.5. Compute that. Get our probabilities. Okay, and you can see, now this time I'm going to once again do from 17 and 27. I'm going to have those give the area in between, and what I'm going to do is I'm going to subtract this probability from 1. So do my 1 minus 0.9115132, calculate the difference, and that's going to be my answer. Okay, so the mean incubation time of fertilized eggs is 23 days. Suppose the incubation times are approximately normally distributed with a standard deviation of 1 day. Okay, determine the 15th percentile. So finding percentiles. Okay. Let's first put our distribution in. 23 is the mean and a standard deviation of 1 day. So when we're looking for a 15th percentile, what we're looking for is what is the number of days such that 15% of fertilizations are less than that. So rather than entering into this first box, we're going to enter 15% or 0.15 in as the probability, and what we're going to compute is a cutoff 21.96 such that 15% of fertilization or egg incubation times are going to be less than that. So I'm going to round to the nearest whole number. That's going to round to 22 days. The middle 97% can be found using the between calculator. The between calculator always is going to, if you type in a probability, it'll always find a symmetric cutoffs, symmetric about the mean. So you can see what we have. Rounded to the nearest whole numbers, it's 21 days to 25 days. Okay, so that's how you can, given a percentage or probability, you can type that in here, hit compute, and it'll calculate the cutoffs for you, either between or standard. All right. Now suppose the lifetimes of light bulbs are approximately normally distributed with a mean of 56 hours and a standard deviation of 3.3 hours. We want to calculate a number of these probabilities. So let's enter our parameters into the distribution. 56 is the mean of the distribution, and 3.3 is the standard deviation. What proportion of light bulbs will last more than 60? More than 60. Click greater than and change this value to 60. Hit compute, and you've got it. This is 4 decimal places. That's 0.1127. What proportion of light bulbs last 51 hours or less? Change this value to 51, and we're looking 51 or less. We're going to less than or equal to. Compute. Oh, we've got it right there already. Okay, I only want 4 decimal places, so I'm going to just type it in. 0.0649, rounded up. Portion between 57 and 62, use your between calculator, put in the first value 57, the second value 62, click compute. That's nice, 34.64%, but I'm putting it as a decimal point, 3464. And the probability randomly light bulb lasts less than 45. So that's back to a standard. The probability that a random light bulb lasts less than 45 is the same as what proportion of light bulbs last less than 45. The probability and the proportion really are saying the same thing. You can see this is 0.0004. That's 0.04%. Very few light bulbs. Okay, so that's how we calculate normal probabilities. Very, very easy. No need to deal with horrible tables. Okay, now we are talking about sampling distributions. So we're looking at, this is a little bit gross, but the acceptable level for insect filth in a certain food item is 2 insect fragments per 10 grams. A simple random sample of 40 10-gram portions is obtained in a sample with a sample mean of 2.6 insect fragments per 10-gram portion. Okay. So why is the sampling distribution approximately normal? Because the sample size is large enough. 40 is a good sample size. A rule of thumb often you'll see is 30, but 40 is probably good enough to guarantee approximate normality. Okay, what is a mean and a standard deviation? If the sampling distribution, assuming mu equals 2 and sigma equals square root 2. This is to say the population has a mean of 2 and a standard deviation of square root of 2. Well, that means that the sampling distribution will have a mean of 2 also. That will also be 2. And the standard deviation is going to be the sampling distribution will have a standard deviation of the population standard deviation divided by the square root of the sample size. So that's going to come down to 0.2224, rounded to 3 decimal places. Okay, now given that, now this is coming from the central limit theorem, but what we can do now is put this into our probability calculator. If we have a mean of 2 for this distribution and a standard deviation of 0.224, we can calculate these probabilities. The probability that we get a value greater than 2.6 for our sample mean is going to be quite small. Rounded to 4 decimal places, that comes out to be 0.0037. So if we actually got 2.6, that is an extremely unlikely scenario, assuming that the mean was 2. So this result is very unusual because this probability is quite small. When we go into hypothesis testing, we would call this a p-value. And the p-value is, in a sense, a measurement of how much the sample data lends support to a null hypothesis. The null hypothesis in this case is that this company is meeting the standards that are allowed. And that probability is quite small, which means that it's actually likely that the population mean is not 2, it's something else. So we would conclude that since the result is quite unusual, it's reasonable to conclude the population mean is actually higher than 2, right? It would be much more realistic if the population mean was, say, 2.5, something like that. Then a sample average of 2.6 would not be such a unusual observation. Great. Okay, so we have a sample, a simple random sample of size 50 obtained from a population whose size is 15,000 in the population proportion with specified characteristic of we don't have any story here. It's just the population proportion is 0.4, 40% of the population. So the sampling distribution of p hat is our estimate of the proportion, also known as our sample proportion. So our sample proportion should be approximately normal. And the reason that is the case is we can check two things. Let's bring up our calculator. We want to check first, is 0.05 times the population size, 15,000. If our sample size was bigger than this, that would be a little bit too large to guarantee normality or approximate normality. And if your sample size is too big, then your sampling stops being independent. Your sample observations stop being independent of each other. But for a sample size less than 750, we don't run into that problem. Certainly a sample size of 50, that's not an issue. The other thing we want to check is if the sample size times the sample proportion times 1 minus the sample proportion, if this is greater than or equal to 10, then this is a rule of thumb, then we should have approximate normality. So both of these are met, so we're going to have approximate normality. Now, the sample proportion is going to have a sampling distribution with a mean equal to the population proportion. So it's going to be equal to 0.4. The standard deviation follows a formula. It's going to be the square root of the population proportion times 1 minus the population proportion divided by the sample size. So everything, it's a square root of that whole thing. And that is the standard deviation of the sample proportion, 0.06928. We need 6 decimal places. So there you go, 6 decimal places. Now we can answer a probability question. Let's type in the mean, 0.4, the standard deviation, 0.069282, and what's the probability that we get a value greater than 0.46? Well, that probability is 0.1932. There we go. Okay, the probability of obtaining 16 or fewer, also known as what's the probability of getting a sample proportion less than 0.32, the same probability distribution. Now we just calculate a left tail probability. There we go, 0.1241. All right, so there you go, the normal probability calculator and some applications in some word problems and some sampling distribution problems. Okay.